Hello and welcome to Lab 6. This is magnetic molasses. Alright, so the purpose of this lab, we're going to observe a magnet falling through a tube of aluminum foil and then measure the time it takes to fall. And then we're going to make a glow script model and then compare those two results. So a preview of our lab, our experimental time was actually very close to our computational time, and we had like less than a 4% error. Alright, so here's some fundamental principles. So we have the Biot-Savart law, which helps us find magnetic field for segments of current. And then we have magnetic flux, which is B times A. And then we have Faraday's law, which says that the EMF is equal to the negative change in flux. And then we have magnetic force. Right, so for the experiment, here's our initial conditions. We just manually took these at the beginning of the lab. So the procedure is we're going to drop the magnet through the tube and repeat it 5 times and then average all those times together. And then the result of that was 0.632 seconds. Alright, so here's the glow script model. So for our initial conditions, it's the same physical characteristics from the experimental part. And the mu mag was from lab 3 or 4, can't remember. So we're using that. So right here is all of our setup, plugging in all those values as well. And then down here, this basically splits the tube into segments, DL segments, so that we're basically just calculating the flux through like a ring at a time. And then for over here, this creates a magnetic dipole moment, which we'll use in the later parts. And then this function calculates the change in flux through one of these rings that we had created over here. Alright, and then for this one, this big loop simulates the magnet falling through it. So as it does, it calculates the change in flux through each ring and sums those all up. And then it's also calculating the force of gravity and the magnetic force, and then setting the F-net vector, and then updating the velocity and position. And then obviously it's just plotting all that. And here's the results. So this obviously shows it falling down. And then here's our velocity versus time graph, and we get a final time of 0.657 seconds. So between the 0.632 and the 0.657, I believe, it was an error of less than 4%. So it was surprisingly low, but the error is still due to inaccurate timing, incorrect physical measurements of like the tube and the magnet, and then an improper dipole moment from lab 4. Alright, finally for this discussion, so what if the resistivity of the conductor were reduced as close as possible to 0? So since V equals IR, if the R is going to 0, the current will reach a maximum, and then higher current or induced current is going to mean that the magnet's going to fall slower. And then if we had cut in holes or slots into the tube, so we have less DL segments of the tube, so there's less total flux, and the induced EMF is going to be lower, which means current will be lower and it'll fall faster because there's nothing to oppose that change. Alright, that's all. Thank you for watching.